People, I hope we're doing well today. In these videos, we're going to be going over the algebra of partial fractions. And I just want to do this in two stages. We'll go over the algebra of partial fractions, and then we'll fold it in with the actual process of integration. So, as I've said before, it's really, this process is just, it's a little more indirect, but it's the undoing of something that you're very, very familiar with. Now, given, if you were in Algebra 2, and you were presented with something like this, and they say execute the sum, or basically simplify by adding these together, you know that basically this is a process of getting a common denominator, right? Just like numerical denominators, you need to basically look at this denominator and say, what factors are here that are not here? And the answer is x minus 2, right? So this one has to be multiplied by x minus 2 over x minus 2. And what factors are here that are not here? And you get x plus 1 over x plus 1. This winds up being 3x minus 6 plus 2x plus 2, all of that over x minus 2 and x plus 1. And this winds up being 5x minus 4 over x squared minus x minus 2. Now, what we need to look at is how do we undo this? Let's say that we were not privy to any of this information up here, and we were told this needs to be pulled apart. We need to undo. We need to, and I mean, it's not official math language, but the best way to describe it is we need to uncommon denominator it, okay? We need to pull it apart into the constituent fractions, or what are actually called the partial fractions, that constitute it. Now, you don't know if this is the case. You don't know what the numerators are in those fractions, but considering the fact that you can factor the denominator into x minus 2 and x plus 1, you do know the denominators, okay? Now, you just need something to sort of hold the place of those numerators. So what we do is we just plop an a and a b up there, okay? Now, we could deal with it like this in fractional form, basically as rational expressions. But if you don't have to deal with it that way, why in the world would you want to? So the process starts by getting rid of the denominators, and the best way to basically the way to get rid of the denominators is multiply through by those denominators. So I wind up with 5x minus 4 is equal to a x plus 1 plus b x minus 2, right? Because when you multiply both sides by the denominators, on this side, you basically have to distribute, right? X minus 2 and x plus 1. When you take this and you distribute it to the first term, the x minus 2's cancel, but the x plus 1 doesn't. When you distribute it to the second term, the x plus 1's cancel, but the x minus 2 doesn't. Now, you can basically find a and b by simply plugging in values for x, okay? If you just plugged in willy-nilly values for x, you would get equations in terms of a and b. And, all you'd have to do is do it twice, and you would get two equations of two variables. You could set up a system and get to work. But when it's something like this, that's so easy, we're going to basically use really convenient values, and we're going to go ahead and let x is equal to negative 1. Because if x is equal to negative 1, I don't get an equation in terms of a and b. I get an equation only in terms of b, right? So this winds up being 5 times negative 1 minus 4 is equal to a, 0, plus b, negative 3. Well, that goes bye-bye. That was kind of the point, okay? So we get negative 9 is equal to negative 3b, and b is equal to 3. Well, we're going to do something very, very similar with a. We're going to let x equal 2, okay? If we let x equal 2, and when we plug in here, we're going to get 5 times 2 minus 4 is equal to a times 3 plus b times 0. That goes bye-bye. Again, that was kind of the point. And we get 10 minus 4, which is 6, is equal to 3a. So a is equal to 2. So that tells us that 5x minus 4 over x minus 2, x plus 1, can be pulled apart into the fractions of a, which is 2 over x minus 2, plus b, 3 over x plus 1. And if you remember, that is exactly what we started with. Now again, this process is a little more indirect, and of course when we get away from factors that are linear factors, it's going to be even a little bit more sticky. But for now, we're going to go ahead and do a couple of examples just with linear factors. And what we are doing here when we use these, what I called convenient values, that is actually known as the Heaviside method. It's named after a guy named Heaviside. And it looks like Heaviside, you know, like he's a little bit husky. But it's actually pronounced Heaviside, at least as far as I know. And basically it's a matter of plugging in those values which make things disappear and make the solutions much, much easier, okay? Now let's go ahead and try it again for this one where we don't actually know the original partial fraction decomposition. This factors, it should be readily apparent that it factors into x plus 4 and x plus 5. Now those factors in the denominator, again, remember, those tell us exactly what the denominators of those partial fractions are going to be. The only question is, what are the numerators going to be? So again, we put an a and a b up there. And not wanting to deal with this as a bunch of rational expressions, we want to go ahead and multiply through by that common denominator. And I get a, x plus 5, and b, x plus 4. Now, in order to find a and b, obviously I need to use x is equal to negative 5 here, and x is equal to negative 4 here. Let's talk about this for just a quick second and what justification we have for just plugging in willy-nilly numbers, right? You need to remember that when we're given equations, oftentimes we're given equations with the express instructions of finding the value of x, or whatever the variable is, finding the value of x that makes that true, okay? What we're doing here is we're finding the values of a and b that make this true for all x. Okay, so if it's true for all x, it's certainly true for any particular x, which is why we can just plug in values of x if we want, okay? And so we're going to go ahead and let x is equal to negative 5, and we get 3, negative 5 plus 10, and a times 0, that makes that go away. That was kind of the point. And you get negative 5 plus 4, and therefore we get negative 15 plus 10, or negative 5, is equal to negative b, or b is equal to 5. Now, we can do the same thing with a by plugging in x is equal to negative 4. So let's let x is equal to negative 4. And we get 3 times negative 4 plus 10, and a is equal to negative 4 plus 5, so 1, plus b times 0. The b falls out. Again, that was kind of the point. And we can solve what we have here. This is negative 12 plus 10, so it's negative 2 is equal to a. Okay, so that tells us that 3x plus 10 over x plus 4, x plus 5 is basically, we can pull it apart into its partial fractions of negative 2. Just be careful that you put negative 2 over the correct denominator, plus 5 over x plus 5. And if you're thinking to yourself, okay, well, how do I check my answer? Well, if you're basically doing the process of uncommon denominatoring a rational expression and pulling it apart into its partial fractions, the way you check your answer is just pushing it back together, right? So let's go ahead and just check our answer real quick. and we have negative 2 over x plus 4 plus 5 over x plus 5. This one we need to multiply by x plus 4 over x plus 4. This one we need to multiply by x plus 5 over x plus 5. And this winds up being negative 2x minus 10 plus 5x plus 20 over x plus 5, x plus 4. And it should be really apparent that we have indeed done it correctly, because that does get us back to exactly what we had at the beginning. Okay, so our answer checks out. This is indeed the proper decomposition into partial fractions. Now, don't worry. You know, you're thinking, gosh, this is easy. Don't worry, it'll get more difficult, I promise. Okay, now, this one, okay, we still have linear factors of the denominator. This is going to be pulled apart as x and x minus 1. So what I need to do is I need to set up 5x plus 4 over x, x minus 1, and that's going to, those factors of the denominator, again, are going to give us the denominators of our partial fractions. Again, the thing that we don't know is what are the numerators that are going to actually make when if I were actually to recombine back into negative 5x plus 4. So again, we don't want to deal with it as a bunch of rational expressions. We want to deal with it in more polynomial form. So we're going to multiply through in order to get rid of those denominators. And I get that. Obviously, the values that are going to help us out the most is x is equal to 0 and x is equal to 1. So let's let x is equal to 1. And we get negative 5 times 1 plus 4 is equal to a times 0 plus b times 1. The a goes away. Again, that was kind of the point. And we get negative 1 is equal to b. Okay, well, that's helpful. Let's go ahead and let x is equal to 0. That's going to be negative 5 times 0 plus 4 is equal to a times 0 minus 1 plus b times 0. That goes bye-bye. Again, that was kind of the point. And we get 4, because that goes away, is equal to negative a, or a is equal to negative 4. Okay, well that means that negative 5x plus 4 over x, x minus 1, is going to be negative 4 over x plus a negative 1 over x minus 1. Now I think you know where this is headed when we actually get to the calculus aspect of it. We notice the fact that this right here is not exactly integrable, but if we can pull it apart into these, both of these make really easy natural log integrals. And that's the whole purpose, right? Remember, I keep telling you, or I've at least told you twice, once in video and once in class, that if we're dealing in this chapter with techniques of integration, that's actually kind of a misnomer, because it's not actually techniques of integration. It's algebra and trigonometry techniques that help us to arrive at integrands which are integrable by the integration rules that we already know. So really, this is employing algebraic and trigonometric strategies, I guess with the exception of parts, because parts were sort of utilizing a prior knowledge of the product rule. But still, you're really learning nothing new about integration. You're simply learning new techniques to changing the integrand. Okay. So let's go ahead. This is negative 6x squared plus 3x plus 5. That denominator factors into 3 linears. We need to factor out a common factor of x first, which leaves x squared minus 1. So what we then have is x, x minus 1, x plus 1. And so now we have 3. And that's not really that big of a deal. You just, instead of A and B, it's A, B, and C. okay? We still need to multiply through by the common denominator to get rid of it, but remember that when we multiply all three of these by the common denominator, when we distribute to each individual rational expression, only one of the factors is going to cancel out. So what you're going to have is when you take all three of these and distribute it over to the first one, the x is going to cancel. The x plus 1 and the x minus 1 will not. At b, the x plus 1 will cancel, but the x and the x minus 1 won't. Over here, the x minus 1 will cancel, but the x and the x plus 1 won't. Well, the Heaviside method still works because every time you plug in one of those convenient values, in this case, -1, +1, and 0, two of them will fall out and only one will be left. Let's go ahead and take a look at that. So let's let x equal to 0. Okay, so that's going to be 5 is equal to a times 1 times -1. And then, of course, when you plug it in here, it's going to be b times 0 times -1 plus c times 0 times +1. Well, both of these go bye-bye, and you're left with a is equal to -5. Okay, let's go ahead and let x equal 1. Well, when I plug in here, I'm going to get -6 plus 3, -3, plus 5, which is 2. So 2, okay, well, that's going to be, when I plug it in, that's going to be 2 and 0 for the factors here next to a. When I plug in 1 here, it's going to be 1 and 0. And then here with c, that's going to be 1 and 2. Both of these go bye-bye, and I'm left with c is equal to 1. Okay, let's let x equal to -1. When I let x equal to -1, still get -6 here, but I get -3 here, which is -9 plus 5 gives you -4. Okay, when I plug in -1 here, it's going to be a times 0 times -2 plus b times -1 times -2 plus c times -1 times 0. A and c cancel out, leaving b, and b is equal to -2. So in each of these three, and you can see it, these two cross out, these two cross out, these two cross out, and what's left is just one of them and a number on the other side. Okay? Now, what that means is that this winds up being -5 over x plus -2 over x plus 1 plus 1 over x minus 1, and that is my decomposition. And if you want to check it, it is correct. You just, multiply this one by x plus 1 over x plus 1 and x minus 1 over x minus 1. Multiply this one by x over x and x minus 1 over x minus 1, and this one by x over x and x plus 1 over x plus 1, and then recombine, and everything just, it winds up being burdensome, but it's not, too difficult. But you do wind up getting what you had originally. Okay. Now, sometimes you're faced with ones that are a little more tricky, like this one right here, because the factorization, if you're honest, is not really all that visible on the face of it, right? But it's easy enough to factor the denominator. If it factors, it's basically going to have, because 5 is prime, there's only a handful of options, right? X plus 1, x minus 1, x plus 5, x minus 5. So let's go ahead and test one of those out. Let's try x minus 5. Let's go ahead and do it by synthetic. 11 and -5. And of course, by the factor theorem, if I get a 0 as a remainder, then it goes in evenly, and x minus 5 is a factor, right? So we'll bring down the 1, multiply it by 5, bring down the -2, multiply it by 5, bring down the 1, multiply it by 5, and oh my gosh, will you look at that, a remainder of 0. But that means that my depressed quadratic is x squared minus 2x plus 1. Well, I know that that's x minus 1 squared, okay? So this winds up being negative 2x squared plus 19x minus 13, okay, over x minus 5, x minus 1 squared. Now, we haven't had a linear repeated factor yet. And what we need to do when we have one of those is we need to put, obviously, a over x minus 5. And you would think, yeah, x minus 1 squared, let's go ahead and put b over that. But you need to go ahead and actually also put c over x minus 1. So anytime you have a repeated factor, you need to go ahead and step it down by 1 degree and put another constant over it. And if you're wondering why, I'm so glad you asked. If you have something like x minus 1 squared, you know that that's quadratic. So its numerator, so in order for it to be like irreducible, like, you know, it doesn't need, it's not top heavy, it's not an improper fraction, it doesn't need to have division done to it. It's actually, you know, it's actually in a reduced form. The numerator can be a constant, but it can also be a linear, right? Okay, so let's just play around with this. Let's say that it is a linear, and I have 3x minus 4, or something like that. The problem is that that is not as reduced as possible. It hasn't been pulled apart as much as possible, because that can be rewritten like that. And the whole purpose of that is that now I can separate the fractions. Okay, and of course this is going to reduce. So if you have a linear over a repeated linear factor, this will always be possible. It will always be possible to change the constant by adding 0 in terms of like plus a minus a, in order to pull it apart and reduce part of it, because this is 3 times x minus 1. So that reduces to 3 over x minus 1 and negative 1 over x minus 1 squared. And since this is always capable of being pulled apart, we, instead of doing something like, ax plus b over that, we actually break it apart and talk about a over x minus 1 squared and then b over x minus 1, okay? So let's do another example real quick. Let's say we have, x plus 2 squared, and then we just have, 4x up here. Well, that would look like, can't really do anything with that. Well, you can actually turn that into 4x plus 8 minus 8. And of course I do that strategically, knowing that if I have plus 8, this is going to factor when I pull it apart and separate the fractions into 4x plus 2 over x plus 2 squared and negative 8 over x plus 2 squared. Again, this basically cancels, and I'm left with something like this. So what I'm saying is you have to basically represent both. Because here's the thing, will there be both? Not necessarily. There doesn't have to be both, but there's a possibility of there being, both the a over x minus 1 squared and b over x minus 1 to the first. And if one of them is if this one is actually not there, meaning that it isn't necessary, the algebra will bear it out, and you'll get a b is equal to 0, okay? So, and we'll talk about this again. We'll talk about this again as we move forward on further examples. But that's the rationale for why I have to have both, okay? Now let's go ahead and multiply through by the common denominator in order to get rid of those rational expressions. And when you do that, on the first one, x minus 5 cancels. On the second one, the x minus 1 squared cancels. And on the third one, only one of the x minus 1s cancel. and you're left with that. Okay, well, I only have 2 convenient values to plug in by the Heviside method, but I have 3 variables. Well, let's actually figure out the ones that we can figure out first, and then we'll deal with the one that's left over. So if we let x equal 1, that's going to be -2 plus 19, which is positive 17, minus 13, which is 4. And you plug in, and it winds up being 0 squared here, and 0 squared. This winds up being -4, and this winds up being c times 0 times -4. Both of these cancel out, and I'm left with b is equal to -1. Okay. Now, we need to also let x equal 5. That's our other convenient value. Well, when I plug in 5, that's a little bit sticky on the left, but it's nothing that you shouldn't be able to do. X squared would be 25. 5 squared is 25 times -2, which is -50. Plug in 5 here. Well, 5 times 20 is 100, so 5 times 19 is 95. So -50 and positive 95. So far, we're at positive 45. Positive 45 minus 13 gives me 32. Okay, well, when I plug in 5 into here, I'm going to get 5 minus 1 is 4. 4 squared is 16. And of course, both of these are going to go bye-bye because both the b term and the c term have an x minus 5. So that's plus b, 0, plus c times 4 times 0. And I'm left with a is equal to 2. Well, I've got 2 of the values. I'm merely stuck looking for my c value. Okay, well, let's go ahead and plug in the a and the b values. So we have -x squared plus 19x minus 13. A is 2. And let's go ahead and multiply this out. This is x squared minus 2x plus 1. And this right here is not b, it's -1x minus 5. But then we still have this c left over here, and this is x squared minus 6x plus 5. Okay, well, let's go ahead and distribute this, and let's start collecting terms. Okay, minus x plus 5 plus cx squared minus 6cx plus 5c. Now, what I'm going to do now is I'm going to collect, and there are more ways to do this than this, but this is one of the ways, and I want to show it to you. I want to collect all the like terms. Well, that's second degree, that's first degree, that's first degree, that's second degree, that's first degree. So x squared is c plus 2 x squared. The x's are -4, -1, that's -5, and then -6c, so -5 and -6c x. And then the constants are 2 and 5, which is 7 and 5c. So 7 plus 5c. Now remember, I said that I'm looking for an a, b, and a c value that is true for all x. If this equation is true for all x, then the coefficients have to be the same value. -2 has to be equal to c plus 2. 19 has to be equal to -5 minus 6c. -13 has to be equal to 7 plus 5c. Now you only have to solve for one of these, but I'm going to solve for all 3 just to demonstrate, right? And you get c plus 2 is equal to -2. -5 minus 6c is equal to 19. And 7 plus 5c is equal to -13. 5c is equal to -20, c is equal to -4, and -6c is equal to, and basically I add over here, so this winds up being 24, so again c is equal to -4. Oh my gosh, well you look at this, they all tell me that c is equal to -4. Okay. And I don't know, like this up here, this is, obviously the Heviside method right here. I don't know what this is called. I don't know if there's an official name for it. For lack of a better term, I refer to it as coefficient comparison. Coefficient comparison, it's descriptive and it's alliterative, so hey, that's fun. But basically what we have here is we have 2 over x minus 5 plus b, which is negative 1 over x minus 1 squared, plus c, which is negative 4 over x minus 1. That is my decomposition. Okay, now, there are ways to do this that involve system of equations, and I'm going to go ahead and do that on one of the ones that follows, but right now I need to go ahead and call this this video to a close. If you have any questions, please do shoot me an email. Bye.